So we have a pleasure to have Professor Chern to give a seminar. Professor Chern has been a pioneer in Taiwan for numerical astrophysics and algorithm development. He was a math professor for many years in Taida, and then he was one of the original co-PIs of our first key project, the PMHD, with Professor Chi Yuan. So it's an honor for us to have him here giving a talk, telling us what he's been up to these days. Okay, welcome, Professor Chern.
Okay, thank you. Can you hear me? Also from this? Okay. Yeah, I taught continuum mechanics last year, which I try to rethink a lot of things about continuum mechanics. So I start to write a lecture note on the fundamentals of continuum mechanics. It includes fluid mechanics, elasticity, and viscoelasticity. Right? So, and I try to use the variational principle to cover the whole thing. Right? So today I will talk about the hydrodynamics part of the lecture note. It is I don't know, to apply mathematician it is still quite theoretical. And I don't know whether it is okay for physicists. Okay, so let's see. The lecture note actually is available on the website. So the outline of the talk include the first is the Newton's description of continuum mechanics, or the fluid mechanics, okay? And then the variational principle in fluid mechanics and the Hamiltonian fluid mechanics. The last part more or less developed probably in the 1980 to 90. Right? So it is still quite late. Right? Okay, so I assume people already know the fluid mechanics, so I just sketch. Okay, so the fluid dynamics in the Eulerian coordinate include the continuity equation, which can be derived from the conservation of mass. Right? So the unknown is the density, the conservation of momentum for the velocity field, and also the conservation of energy for a thermal quantity, for instance, the entropy or the internal energy. Right? So the unknown include the density, right? Or V, which is 1 over V. 1 over rho is the specific volume, the entropy, the pressure, U is the internal energy, and the sigma here is the stress, which is minus Pi for the gas. Right? And E is the total specific total energy, included the kinetic energy and also the specific internal energy. And F is the internal body force. There are 5 equations. Right? So this is 1, and this are 3, and this is 1. For the 5 unknown, the velocity field, which is 3, and also 2 thermal quantities, and plus the equation of state, which leave only 2 independent thermal variables. I can just. Oh, okay. Okay.
How many equations of state do you use? It depends on the
equation of state. Equation. Usually there are 2 kinds of equation of state: caloric and the kinetic. Okay. And but it's eventually we have only 2 independent thermal variables. Right? So here I assume I just use.
For example, if you introduce temperature T, you need one additional equation of state to close the hydrodynamics.
Yeah. Yeah. Here the way I write is I just use the internal energy is a function of V and S. I did not put the temperature here. Right? And I assume that U is equal to CV times T. Okay,
Yeah.
for instance.
If you
Yeah, so
if you consider heat conduction in the energy equation, then you another some variable
Yeah.
T appears.
Yeah.
So you need additional.
yeah, right, right. So there are two kinds of equation of state. Yeah, kinetic part, and another is the which relate some kinetic to the thermal variable. Another is the caloric part. Okay. So and usually there are 4 of them, plus these 2 equation of state. So they are eventually only 2 independent of thermal state, right? Thermal variables. Right? So which is shown here. Right? So anyway, I have this Euler equation. I have 5 equations and 5 unknowns. Right? And I will skip the derivation. Okay? This is based on conservation laws. Right? Conservation of mass, momentum, and energy. Okay? And so usually we write this in abstract form. So the dTu plus divergence of flux equal to some source term. Right? So we write in this way. Okay? And physically, actually, this is better to write in the integral form. The integral form can cover the discontinuous solution, which is the weak solution. Right? And but usually in the differential form, we need to interpret this as a weak derivative. Right? But in integral form, it is okay. Right? Then I go to the conservation law in Lagrangian coordinate. Okay? The Lagrangian coordinate means suppose this is the fluid, and it evolve into this through this flow map. I call it phi t, phi sub t. Right? So the Eulerian coordinate, I denote it by x. Right? So and the capital X is the Lagrangian coordinate. So x equal to phi tx, or sometimes I denote it as the flow map is as the x of t capital X. Right? So this is the flow map. If we know the velocity field from the Eulerian formulation, then we can integrate it, and then we can obtain the flow map. On the other hand, if we know the flow map, we take a derivative in t, then we know the velocity field. So if we know the flow map, which is equivalent to we know the velocity field. Right? So this is so I call x as the Lagrangian coordinate, and small x the Eulerian coordinate. Okay? So I want to change this equation, transform this equation into the Lagrangian coordinate. And there are 2 main theorems for this transformation. One is called the Reynolds transportation theorem. Right? So it is this form. Right? So it's integrate of ftx over omega t. Omega t is a domain, right? And move with the fluid. Right? The change of this equal to one is you differentiate inside, another is you differentiate on the boundary. Right? If you differentiate on the boundary, then you have a flux term. Right? So this is called a Reynolds transportation theorem. Another is the surface integral. The surface integral, if you transform it back to the initial time, then you have some quantities. One is the Jacobian, another is called the deformation gradient. This f is the dx, where is the Jacobian of the Eulerian coordinate with respect to the Lagrangian coordinate. Right? So it's called a deformation gradient. So you have this. With this tool, then you can just transform. You can get the conservation law in the Lagrangian coordinate, which is the original one in the Eulerian coordinate, back to the Lagrangian coordinate, which can be written in this form. Okay. So it is this rho 0, rho v, and rho e. Okay. You just take a rough look at this. But in this equation, right, the rho 0, which is the initial mass, initial density, this equation here, the first equation is a trivial equation, right? So it's irrelevant. So only 4 equations in this formulation. One is this the momentum equation and also the energy equation. Okay? So there are only 4 equations here. So what are missing? The missing part actually is the deformation gradient. Okay? You need to put all the deformation gradient in. Okay? There are 9 equations for the deformation gradient. Okay? So you differentiate them, and then you get this equation. So there are 13 equations with 13 unknown. Right? So this is much more complicated than the original Euler one. Right? Usually, for people working on elasticity, they use Lagrangian form. They need to use the Lagrangian form. It's more complicated for them to use the Eulerian equation. Right? But in the fluid mechanics, people usually use the Eulerian coordinate because it is much easier. Right?
So if you go from 5 to 13, you have 8 more unknowns.
I have 8 more unknowns. Actually.
So you got 3 coordinate changes, like 3 unknowns.
Yeah.
And then.
Well, because I need to put this f in. Right? The f is the deformation gradient. It's the Eulerian coordinate, the derivative of the Eulerian coordinate with respect to the Lagrangian coordinate.
Jacobian.
The Jacobian. Yeah.
3 must be 9.
9, yeah. That is 9. Yeah. In fact, we have even more. There is a consistent constraint, the dFi alpha, the derivative of this with respect to x beta equal to this. Okay, this is called a consistent condition. Right? So it is automatically satisfied in the differential case. Right? Well, in the differential equations sense, then this is automatically satisfied. But if you put it into the computer, if you solve these 2 equations, 2 set of equations, this may not be satisfied. Right? So sometimes there are errors, and this error usually create big problem. So are these 2 formulations equivalent? Okay? They are equivalent as long as the flow map, xt is Lipschitz continuous. Okay, xt is there is no discontinuity. When do we have a discontinuity for x of xt, tx? When the flow map was splashing, okay? So usually if you see some simulation, you will see like you have a wave break, then you can see this x, this flow map actually is discontinuous, right? But in that sense, then these 2 formulations are not equivalent, okay? But the question is, well, as long as this flow map is Lipschitz continuous, they are equivalent, okay? I give a warning on this. In engineering application, usually people write in this form, okay? Call this as a Lagrangian formulation, right? The first one. Right? I don't know, there is a pointer of there's no pointer for this.
Sorry?
Yeah, oh, okay. I can see. Okay, yeah, there is already a pointer. Yeah, okay. Yeah, in engineering community, they call this some Lagrangian formulation, okay? So they move particles according to this. In this formulation, the d dt actually is the material derivative. Velocity is in the Eulerian coordinate, and so this actually is Eulerian, right? And also dxp, this is Eulerian. So this actually is a Eulerian formulation. But if you go to the real Lagrangian sense, it is this form, right? Not this form. Right? A popular numerical method called SPH, smooth particle hydrodynamics, or the semi-Lagrangian method. They all use this, but sometimes they use this to have some to simulate some spacing, okay, which I think it is very dangerous.
What is splashing?
What?
What is splashing?
Spray, well, like wave break, okay. So fluid separate into two parts or many parts, right?
Kind of sharp. These are really sharp.
You
said that stronger continuity than a sharp.
yeah. Let me show you this is called, they call the spray, the wave in the wave breaking. Yeah, this kind of thing is this is then break, and then you have a overturn of
What is the
some.
ordinate and opposite sign?
What?
What is the opposite sign and ordinate? Horizontal and vertical axis.
Can you repeat your question?
Would you show me the horizontal axis and the vertical axis?
The x and the y axis, and this is dam break. So the dam break and the water flow down, and then there's a wave break. And then they say
the wave kind of detaches from the bulk of the flow. It separates.
Yeah.
So that's what you
Yeah.
call
So-
the splashing.
Yes,
Yeah.
something is called splashing, that kind of separation.
Yeah, or like this. Okay, but I think I do not trust this kind of
If I'm
simulation.
into crazy, you can even have merging, which surely will be no better.
Yeah, but all of this, the flow map is discontinuous. Okay, and I think this is this is not this continuum mechanics covered. Okay, this should go to the kinetic equation or some kind of kinetic equation. No. How do I go back? Okay. So as long as the as long as the flow map is Lipschitz continuous, we are safe, right? And we are allowed to have a discontinuous of density, velocity field, entropy, right? But we are not allowed to have a discontinuous on the flow map. Right?
So shocks completely allowed in principle.
Yes, can be very large. Right?
You cannot
Shock is
detach
allowed.
The flow.
Yeah.
That is the connection between the Eulerian and the Lagrangian coordinates has to be continuous.
Yeah. In a gas tube, if the flow run opposite direction very fast, there is a vacuum. Right? I don't know whether it is in that it's still in this formulation. They should be should be equivalent, right? But flow are separated, right?
Yes,
There is a vacuum.
formation of a vacuum.
Yeah. Okay.
Certainly, SPH will have numerically problems in formation of vacuum. The
Yeah.
extreme,
Yeah.
but that's numerical question.
Yeah. In the Riemann problem, you can solve this Riemann problem with vacuums
Yeah, that's
state.
the solution. Can happen in every problem.
Okay, next I will go to this. No. Okay, I'll go to this topic. So the fluid dynamics in terms of the language of differential geometry. Right? The main things I want to talk about this material derivative and Lie derivative. Right? Material derivative is commonly used in fluid mechanics, but they are mainly for scalar field. Right? It is generalization for the vector field and also tensor field. Actually, it's called the Lie derivative. So I want to clarify the idea here. Okay, so what is the material derivative? Material derivative means a function which is this t and x. Okay, but x is the flow map. So the derivative of t of f in t with a fixed the Lagrangian coordinate can be written in this form. Yeah, so it's f sub t plus x dot and df dx, which is written in this form. Right? So this is usually called a material derivative. Yeah. So I write either d dx with a fixed x, or sometimes I do not write. I do not put down the capital X. Just write d dt. Right? But if I use a partial t, which means the Eulerian derivative in t. So material derivative for physical quantities, you can have many. Okay, yeah. In particular, this ds dt equal to 0, which means the flow is adiabatic. Right? But let's see the change of vorticity with the fluid. Okay, so if you take some effort, then eventually omega is the gradient curve cross product v. So this is the curve v called vorticity. So you can derive the equation for vorticity, which is this material derivative, and then plus two more terms equal to this. So this equation actually is very interesting. Right? So this is the convection term. This is called a vortex stretching term. This is the shrinking expansion term, right? And this is the thermal production term, right? So all the right hand side is this kinetic part, and the right hand side is the thermal part, right? So which means well, the change of vorticity, well, it's real complicated here, right? But it's due to this thermal effect. It's called a buoyancy effect, right? Right? But all this part actually can be written in terms of Lie derivative. It is just the Lie derivative of the vorticity. Right? So it has meaning is this. So let me make some explanation of what is the Lie derivative. Right? So first, we need to have this the concept of pullback. Okay, phi is the flow map, right? And the phi t pullback star means the pullback. So it applied to the scalar field, which is phi t star f is nothing but f t xt. So pullback means originally it is in the Eulerian coordinate. Then you pull it back to the initial time, right? So phi t star f is defined at initial time m0, right? So it is t capital X, right? So it is nothing but f t and the flow map. Right? So we call it you pull back from the Eulerian coordinate back to the Lagrangian coordinate, the initial time. Right? Then when you go back to the initial time, then you take derivative, and then you push it back to the Lagrange Eulerian coordinate. Then you get is what you get is called the Lie derivative. Right? So the Lie derivative for the scalar field is the material derivative. Right? So we call this as the zero form. Right? But let's see what is the other case. Right? So in fluid mechanics, we we measure the circulation quite often. So let's see how do we measure the how do we pull back a circulation. So let's this eta is called eta I dxi. This I means sum over all I. Right? So if I take this eta I to be the velocity vi, so then this eta I vi dxi and integrate over a closed curve, right, which measure the circulation of this of the any object is surround. Right? So let's see let's measure this circulation and see how it's changed in time. Right? So we differentiate this. Right? So when we differentiate this, we first pull all this back to the initial time. Right? So this eta I t, then tx, and then this dxi is pulled back to, is changed to this. Right? And then we differentiate it. Right? So differentiate it means we fix capital X. Yeah. So we differentiate it, then eventually we change back to the CT. Right? So we differentiate and then go to this, and then eventually what we get is this dt and plus this, and then plus additional term. So this part is the material derivative of di, but this additional term is this one. Right? We call the whole thing is the Lie derivative of this one form. Right? This is the velocity one form. Right? So this one form, the Lie derivative of this one form is defined to be this one. So it's the material derivative of this and plus this additional term. But the concept is nothing but you want to measure the change of circulation with the fluid. Right? So it's just first pull it back to the initial time and then take a derivative and then push it back to the time t and then see it is a form, and that form is called the Lie derivative of this velocity field. If you go to the two form, right? Two form means like vorticity. A vorticity is a two form. Right? It's a omega 1. It's this form. Right? And you do the same thing. Okay, pull it back to initial time and differentiate it, and then push it back, and then you will see is this form. Okay. Right. So the complicated term here is nothing but we pull it back and to the initial time, differentiate it in t, and then put it back. This is what we get. So the mathematical concept is simple. Right? The form looks complicated. Yeah. Okay. So we can write down the Euler equation in terms of the Lie derivative. The first one is the Lie derivative of the mass is 0. The second is adiabatic. The Lie derivative of the scalar field, the entropy is 0. And the equation of motion can be written as the co-velocity. It is again called one form. Okay, the Lie derivative of this co-velocity is equal to this form. Right? And the vorticity equation is this one. Okay, equal to either this one or this one. These are called the thermal surface area element. Okay, either use dt wedge ds or the dp wedge dp, depending on the velocity, the variable you use.
The co-velocity is the divergence. Is it?
What?
The co-velocity is the same as the velocity divergence.
The what? Which one?
So your equation of motion, you've got vorticity equation, which is 2 degrees of total of 5, right? So you've got mass is 1, adiabatic is 2, and then you've got 3 more. So the
You mean this one?
yes, that's 1 degree of freedom.
Yeah.
And then the vorticity is 2 degrees of freedom. So the total of 5, right?
Yeah, no. Independent equation are only this 3. Yeah. So I put this blue, but I put this. So the Euler equation is only this 3. Yeah. 3 equation. I put this additional one, but I do not put it in the in blue. In blue. Okay.
That's implied by the first 3.
Yeah. So my Euler equation only this 3. Yeah. And it is a coordinate-free formulation. Right? Let me turn my gear to this Kelvin circulation theory. It plays a very fundamental role in hydrodynamics. Right? So from this vorticity equation, or is this one? Right? If the thermal variables has only one independent thermal variables, I call it thermal degeneracy. For instance, P and rho are functional dependent. Okay, so barotropic flows are one of this example. Right? In this case, then this right-hand side, the right-hand side is 0. So the vorticity is conserved. Then you can see is if you measure the circulation. If you measure the circulation, the change of circulation with the flow map is 0, right? And that the proof is easy, right? You just use this the dt dt, and this one is equal to the vorticity field over this one, and this is 0. And the vortex filament, vortex tube, the dynamics of vortex tube are very important, play a very important role in fluid dynamics. Right? So there are a number of results which are mainly derived from this circulation theory, but I want to mention only 2. Right? So other vorticity theorems, one is Helmholtz vorticity theorem, another is Rattel's potential vorticity theorem. Okay. So Helmholtz vorticity theorem is about the transportation of omega over density. Another one is the conservation law of the omega dot gradient S over rho. Right. So it's this. Right. And they can be, okay, so I use a PD way to derive this. Right. So we recall this equation, vorticity equation, this. Right. But the specific volume, V is 1 over rho, is the specific volume. Set by this continuity equation. Right? This part, the blue part, okay, both involve a divergence of V. Right? So I can use V times this times V and this times omega, and then add them together and then cancel this 2 term, this term. Right? So this is the way I remove this expansion shrinking term. Right? So what I get is this one. Is I get this one. Right? So no more this kind of term. Right? And if you write in terms of density, then you get omega over rho minus this equal to this. Right? So what is important here? This is called a Helmholtz vorticity theorem. In the case of thermodegeneracy, for instance, the barotropic flow, right? Then the right-hand side equal to 0. Then what is this one? Right? This one, let me just write here. Right? So it is this. This part actually is the omega over rho. It's just like a vector. Flow is it's just like a tangent vector transport along the flow. If you consider OD, the ODX dot equal to velocity field Tx, okay? And the variation of this OD is actually give you this equation. Okay? So which means this omega over rho is just the tangent of the flow map. Right? So it play a role as a tangent vector. Right? And then a lot of consequences I get at least here is a consequence of this Helmholtz vorticity theory here. Right? So
in a if vorticity is vorticity has velocity has 3 degrees of freedom, and vorticity only has 2, right? Because it's divergence free.
No. Vorticity field has also 3 independent
components, but it's divergence free, so they only. Well,
okay.
No, I can. At least I think in our language we usually say, oh, any velocity field that can decompose into a divergence and a curl.
Yeah.
And the divergence is 1 degree of
Yeah.
The curl would have 2. And just to see if I follow this tangent vector. This Helmholtz vorticity theorem makes a statement that of this vorticity vector, there's one component which is conserved along the path. So it says that I have one of these 2 degrees of freedom is conserved and the other one is not. And that's the right interpretation.
Yeah. Okay, good. Yeah. Good. So if I treat this as a vector, the derivative of this equal to 0. Right? Another is Rathel's potential vorticity equation. Right? I think in 1942 derived another quantity. Right? Say this called a potential vorticity. He said, well, this quantity it's a scalar field. Okay? It is a transport with along the fluid constant. Right? It's invariant. Right? And so the derivation again is also simple. Recall we have this. Where is my? Oh, here. Yeah. The Helmholtz vorticity equation this form. Right? So we want to remove this away. Right? So, but we recall. The idea is this. He introduced a quantity called psi, right, which is a free artifact thermal variable. So 2 requirements. The gradient psi dot, this equal to 0. Right? So if you take inner product with gradient psi, it's equal to 0. Another is psi is freely artifacted. Right? So it's this quantity. It's this. If you define C equal to grad phi, then you take the gradient of these equations, then you will get this term, okay? Which is again they have the similar term, okay? So you times this example of this sign is for instance entropy or potential thermal temperature. Right? They are many, right? But these 2 are the main 2. Right? Right. So you define Q equal to omega dot gradient psi over rho. Right? and then you can show dq, dq dt, the material derivative of q equal to 0. Q is not a scalar field, right? And the proof is simple. It's just this one you take the where you just add these two. Okay, one is you times dot c, the other is you dot omega. Add them together. Right? Okay, so this is a tail. Right?
So if I follow again, so if S is constant, therefore gradient S is 0, then you have Kelvin circulation theorem holds, right?
Yeah.
Which allows for conservation of the full vorticity. The you've got two degrees of freedom that are Lie derivative is conserved along the flow. But if S is not constant, then you have instead this quantity, only 1 degree of freedom now is conserved, and the other one you've lost.
Yeah. Yeah. So this this thermal this buoyancy in turn is cancelled through this thermal this is free advective thermal parameters. Yeah. So but still there are a lot of choices.
So let's go back to counting again.
Yeah.
So we started off. So Euler equations is 5 equations and 5 unknowns, and it's a conservation law. Right?
Yeah.
So again, I'm not actually I don't know what happens in 3D, but in 1D at least in the conservation law, I can take the Jacobian of my partial axis and diagonalize it, and then I get a bunch of advection equations for n conserved variables, which presumably happens in 3D as well. So presumably there are always 5 conserved quantities, or is that not true in 3D?
Yeah.
And then in this case, this would be Ertel's potential is one of the 5. And of course, instead of mass and entropy, right? But mass is always conserved. Entropy, well, entropy is conserved along your flow line in the absence of discontinuities. And then you have Ertel's vorticity is conserved always, even when you're not isentropic. And then there's one more. Is that right?
But they are dependent. I think this equation actually, they are derived from the momentum equation, and so.
No, I follow. I mean, there are 5 equations. You're not gaining anything, but you can.
Yeah. But it seems you have more equations, but they are consequence of the.
These things connected to Kelvin's circulation theorem often have different behavior if we add the viscosity terms, because for momentum conservation, adding the viscosity term changes the equation by adding one term, have to viscosity, very important, but essentially the equation stays. Many of these equations stop being conservation loss in presence of viscosity, if I remember right.
No, but there is no viscosity yet.
Yeah.
Zero viscosity.
Exactly. That's exactly what I mean. That's exactly what I mean. There is a conceptual difference to sense them between these conserved quantities and the momentum conservation. These conservation laws are more fragile in the presence of viscosity. You're correct. Here we have no viscosity. So they have free strength.
I agree, but I think I was trying to ask a more mundane question, that in smooth flow, entropy is also conserved along the flow line. ds dt is exactly 0, and you're saying that also not robust, because if you have shocks, of course, that is not true. But nevertheless, if you think of just a what do you call it, a hyperbolic equation. Right, hyperbolic equation, a general statement is that you've got some initial data, and I want to know the data at some future point, and I just go back to characteristics, and then the final data is just equal to the domain of dependence of my initial data, and then normally we say there are three characteristics only, as plus or minus sound wave, and then along the flow line. The plus or minus sound carries 2 degrees of freedom, and the flow line carries 3. Normally, I think that's what at least in the physics interpretation of it. So the 3, I'm going to count these here, right? So entropy is always carried along the flow line. And then we need 2 more. So this atom potential is also carried along the flow line. And then there should be 1 more, I would think, or maybe not. Maybe I'm not thinking the right way.
I don't. We can count it. We can count later because I will go to this question again.
Okay, thanks. Maybe we
yeah.
should keep going then. Thanks.
Okay. So well, still.
I think you have to solve that question. So keep going.
Okay. Okay, variational principle in Lagrangian coordinate. Okay, so this part will go very fast. Okay, so we define the first the configuration space. Again, is this flow map, yeah, the Q or the X, right? And so the action is the kinetic energy minus the potential energy. I write the potential energy as a function of a deformation gradient. And then variation of the action with respect to the flow map, which will give you the Euler-Lagrange equation, which is the equation of motion. Right? So, and then you can check that this equation of motion actually is the same as the one we derived in the Euler framework. Right? So. Then the next question is, can we derive these equations in the Eulerian coordinate, which means that the action is defined as a function of the 2 thermal variable and the velocity, which is this form. The previous one we write in the Lagrangian variable. Okay, so it's the x dot and is this one where I write this. The original I write in this form, right? But now I write, so the original one is the flow map, is the unknown. But now the unknown is is this one, right? So there are 2 approaches. Okay, one is called the dynamically accessible variations, right? Or the Euler-Poincare Hamil's approach. The other is Harville and Lin Jiaqiao's approach. Right? It's a constraint variational approach, which will I will answer the number of unknowns. How do we count that? How many unknowns do we really need? Right? So yeah, so they have these questions. Before. So the variation of the of action in Eulerian variables, right? So it's this one, right? So these 3, the variation of this variable are not arbitrary, right? So the real variation actually is the flow map, right? So we consider the variation. So given x tx is a flow map, and then we take a variation of this called xs tx. Okay, and this xs tx, they have to satisfy 2 more constraints. Right? One is the density constraint. Right? So along this the variation, they should conserve the mass. The other is the entropy should be conserved in both T and N as well as S. Okay? Then you take a variation. The variation is the variation of this flow map with respect to S. Right? And then you define what is this W and the corresponding V and the variation of density variation of S. Right? That is all due come from the variation of the flow map. And then eventually you will see is go through this variation, you will see the variation of S with this constraint, with this dynamically accessible variation, give you this form. One is this, the other is this. This one actually is the first law of thermodynamics. This one is actually the momentum equation. Right? So this variation gives you everything. Right? The other is a Halliwell-Ling's approach. The idea is the following. Right? We have two constraints: density constraint and entropy constraint. So we write the variation of the action and the plus we use the Lagrange multipliers to put these two constraints into the variation. Right? But then people find this the solution to this Euler constraint or variation cannot recover all solutions of the Euler equation. All the solutions has zero helicity. Right? So this is not enough. Right? And Ling Jiaxiao find there is another constraint we should put, which is he say the equation actually is invariant under so-called particle relabeling. Right? So if you change the so the x is the Lagrangian coordinate. They also set it like this. So we should put this into these two constraints. Okay? So he consider this kind of variation here. Yeah. I don't know. This. Oh, okay. The pointer sounds, yeah. Still? Oh, okay.
Anytime you want, you can just right click and it will just show up.
Oh, okay. So this is the Lagrange multiplier corresponding to the density constraint, and this is for the entropy constraint, and this is for the relabeling constraint. So gamma is the Lagrange multiplier, gamma, phi, and also beta. Right? So with this, then you can, the Euler Lagrange equation give you several terms. One is the equation is an equation for V, right? Is this form. Another is the dynamics of this Lagrange multipliers. So the meaning of this is this Euler Lagrange equation actually give you a representation of the velocity field in terms of the gradient phi, which is potential, is a gradient of a potential, yeah. And also this two, okay. And this is called a clash representation of a velocity field, right? And all this gamma x are all called clash variables. They move along the fluid, right? They just follow the fluid. And the number, I skipped this, okay. But anyway, you can show is with this, then they recover the Euler Lagrange equation. They recover the Euler equations, and also they can represent all kind of velocity field. And the minimum amount.
On the comment of variational derivations, I forgot which book it was, some GR textbook. So they just say that in general relativity, if you have any fluid, your action is just rho. Is for relativistic fluid, it's just the rest mass times gap, whatever you use for it. But then you say, okay, so how do I get the equation of motion? I require that the variation to the metric is zero. Even the metric is empty space, and I think that's similar to this statement, right? I want a relabeling invariance. Which is the same as in relativity. You say I want the general coordinates invariance. then the variation of your action to just metric, even if the metric is constrained to be Euclidean, gives you T mu nu divergent equal to 0. Okay, that's the Bianchi identity. And that gives you 4 equations of motions, which is for relativistic fluid all you have. And if you want to have a Eulerian fluid, of course you have to add in that the SDT is 0. So isn't that just, aren't these all special cases of just the generic GR variation statement? I mean, these are just roundabout ways of saying the same thing that the textbook says, oh, it's a one-line, in GR, this is just a one-line obvious thing, and then you plug back saying that my metric actually is just Minkowski.
Well,
I think.
Well, I don't know. I can.
I cannot consider the non-vanishing Riemann tensor plays an essential role in deciding. Basically, GR and SR are essentially the same, as long as we consider linear coordinates. The only difference is whether Riemann is vanishing or non-vanishing.
Exactly, but you say it's a trivial case, and it's a variation, and then it's set Riemann tensor to 0, and then you get this back with 0 work, right? If you have 0 work involved, you just say variation S for T mu nu, and then you get T, like the identity gives you T mu nu equal to 0, T is rho u alpha u beta, and you're done. So it's a one line, no work involved, and you get the same answer, and I think it's the same assumptions. You can now see why you need this, because coordinate relabeling invariance is just coordinate invariance. So that seems to be a very quick way of getting the same answer and under the same assumptions. And then the SDT is just saying if you want in addition to energy conservation a particle number conservation like entropy, then you put that just like here, you put it in addition. I think. It seems to me these are all special cases of just the
modification is not very large.
What?
Modification is not very large.
I know, but it makes a one-line derivation, and you don't need any justification anymore.
Yes, covariant derivatives do not commute. So, for instance, divergence of vorticity does not lie, for instance, in the current space-time. But the correction is minor.
I think we're talking about a mathematical question, a derivation. How do you get an equation? How do you give an assumption, and then a derivation and an answer, right? And here I think Professor Chern gave us.
We are thinking in terms of a formulation GR plus hydrodynamics together in a single theory, creating an action principle covering both. And variation will cover both Einstein's equations and the equation of hydrodynamics.
Anyways, let's keep going.
Let me continue.
Excuse me. Why the velocities depend on the entropy? It's very.
What? Why?
The equation 20. The velocity is in terms of is a function
Equal to
of
this?
Entropy.
Okay. This actually is derived. Yeah, is here. Yeah, and they are derived from the variation of the action with respect to the velocity, which will give you this. Well, the S I have this original action plus the constraint, right? And then you just take a variation of this S with respect to V. Then you get when this is equal to 0, then you get a representation of V in terms of other variables. In particular,
to my eyes, of all these terms, perhaps the most intuitive is the last, because the idea that velocity is in some sense the gradient of a flow position sounds intuitive to me. But maybe I'm misunderstanding something about this equation, the representation of V.
yeah.
Something like that.
Yeah. Originally, without the additional relabeling constraint, then the representation of V is equal to gradient phi plus beta gradient S. Right? That is without this relabeling constraint. Okay. So well, it's from here. Yeah? So the S equal to this. If you do not have this term, then if you take a variation of S with respect to V, then you get a a representation of V. But without this, all this, yeah. So that is the original one. So that's the original, original one. But mathematically, if the V is in 3D and this is enough, this is enough to represent an arbitrary V, velocity field. You need additional one. So that is the dark box theorem. So you need to have others. So K need to be greater or equal to 1 in order to represent a general V. So general V means also means the curve of V is vorticity. So which means arbitrary vorticity field. Right. So if you want to represent the arbitrary vorticity, arbitrary velocity field, you need to have K at least equal to 1. So which means the number of parameters to represent V is 5. There are 5. Right? One is this phi and beta s, and then C1 eta 1. Right? So the 5 of them. Once you have 5 of them, they are independent, and they are at a function. They are at a vector with a fluid. Right? So S C eta all at a vector along with the fluid, and then you just rewrite the Euler equations in terms of another variables. Okay, another 5 independent variables. Okay. So this is another way to represent the Euler equation, called a Lagrange representation. Let me go to this relabelling symmetry. So I just put the keywords here. Okay, mass, entropy, and velocity preserving relabelling. Right? Give you the conservation of potential vorticity. Right? So what means the mass, entropy, velocity preserving relabeling? Well, you consider an infinitesimal relabeling by this x hat equals to x plus delta x t x. Okay, and the x hat equal to x. Right? And this is a change of variables. Right? Infinitesimal relabeling. Right? And then if this change of variables leave the corresponding Euler Lagrange equation unchanged, right? Then we have a symmetry. But this the relabeling symmetry need to satisfy the you do some calculation, then you will see they should satisfy this 3 conditions. One is the conservation of mass, and also entropy should be unchanged, and also the velocity field should be unchanged along the variation direction, the relabeling direction. With that, then a natural choice of this is this gradient x S0 times this and then over the, and this you plug this into this Lagrange, and eventually using the North's first theorem, eventually you will get what you will get is the conservation of potential vorticity. So this potential vorticity can be derived from the relabeling symmetry. Right? This particular relabeling symmetry, mass, entropy, velocity preserving relabeling, right? Through the North's theorem. Right? Okay. So why?
Maybe you should use these. Maybe you should use the laser instead, like that.
Okay.
Otherwise, maybe they may not be able to see the case.
Yeah. Okay. Why variational approach? In Newton's equation of state, it is a force balance equation. Yeah. But in the variational approach, the forces are derived from variation of energies. So we use energy to unify everything. Right? Forces are derived from energy. Force is a variation of energy with respect to flow map. Right? And energy can also unify the first law and also the second law with this Newton's law. Newton's law of equation of motion. So it can also be used to find the invariants. Energy control, topological invariance stabilities. Right? And from Noether theorem, the relevant symmetry give the vorticity theorems. Right? And the variation also give us the Crash representation of a velocity field in terms of Crash variables. And the dynamics of Crash variables are simple. Right. So I'm going to go to the last. Oh, this is just a remark. Okay, these are recent paper. Cauchy is almost forgotten Lagrange formulation of Euler equation for 3D incompressible flow. Actually, the vorticity equation or the circulation theorem were derived by Cauchy in 1815, and then re-derived again by where you can see this paper. Eventually in 1609 by Kelvin. Yeah, and there are many. There is a history about this theory. Right?
Kelvin's circulation theory was previously much earlier discovered by
they were rediscovered several times. Okay, the last part, the Hamiltonian mechanics, fluid mechanics. Okay, so the well, let me skip this. Okay. Well, so the Hamiltonian dynamics is mainly we want to define so-called Poisson bracket. Okay, first we derive the Poisson bracket just mimic to the classical mechanics. We use Q and P, and then just put one more parameters, the capital X. Okay, the Lagrangian coordinate, and then you can get the Poisson bracket is this form. Okay. Right. And this. But so this is called a Poisson bracket in Lagrangian variables. But now we want to derive the Poisson bracket in Eulerian variable, which means we will use the density, the entropy, and also the momentum. Right. So then we use the transformation from the Q and the P to these three variables through this transformation. And with this transformation, then we can define Poisson bracket for these variables. Right. So eventually you can get a Poisson bracket in terms of rho SM or in rho SV. Right. Okay, so all this can be derived, okay? And they are equivalent to the original Euler equation. Right? But the Poisson bracket in the Eulerian variables is degenerate. Originally, the Poisson bracket in the Lagrangian variables, they are 6 Lagrangian variable, Q and P. But the Eulerian variable, they are rho S and V, they are 5. So you expect the Poisson bracket in Eulerian variables is degenerate. So you can check, and then we call a function C as a function of rho as V. It's called a Casimir invariant if it is a Poisson bracket with an arbitrary f, arbitrary function f is 0. Right? So then you can derive the function C. You can derive an equation for this Casimir C. Right? So it satisfies this. A particular example of a C is either C is a function of V only, then you can find this CV has to be this form. It's called a helicity. It's measure the linkage or the nullness of a vortex line. Or you can define Q equal to this, and then C is defined to be this. This again is another Casimir, or this. Okay. There are many Casimir, which means this all the equation, actually there are many invariants, right, can be derived through this Poisson bracket approach. Right? So finally, let me give it the final comment on this. Hamiltonian flow mechanics in Eulerian variable has many beautiful mathematical structures, right? Like Poisson bracket, Casimir invariants, Noether's conservation laws. Right? There are many geometric integrators, right, available, which can preserve the symplectic structure. Casimir invariant and Noether's conservation laws are less explored in discrete form. Previous one I only talk about the continuous case, right? But the discrete case is less known. Right? And however, the Hamiltonian flow mechanics cannot be applied after shock formed. Right? When the shock is formed, then there is a basic assumption about when you define this Poisson bracket, there is a smoothness assumption behind. So after the shock formed, then all this is breakdown. So you have to go back to the to some dissipative system and take the limit, and that part is less developed, right? And also the discrete sense. In the discrete sense, whether you have some scheme which is monotone, right, and then preserve some structure which is not known. Right? What's happened for the Casimir invariant after shock? Right? Well, this is not known. Right? So the topology may change. Right? Or when the topology is changed, then what is the Casimir change? How the Casimir change? This is also not known.
Is that even an issue in 1 plus 1 dimension?
Huh?
Is that even an issue in 1 dimension?
Well, that is not one-dimensional. I don't know. No. I think the Casimir in I think that is trivial stuff. Yeah. I think the meaning for one is still 3 dimension. Especially you can start to understand that I don't know.
I have a question.
I think 3.
I have a question.
Yeah.
About your point 4.
Huh?
So, say for example, if we just solve a shock-based flow, say 2D shock.
2D shock, yeah.
And we solve it in a very highly accurate finite difference or finite volume solver. And then from the solution, we recalculate the functions in Hamiltonian system. and then try to calculate the negative part to balance the system.
The negative part.
Yeah, but so the negative definite.
What is the negative?
You see, what I'm saying, that we can recalculate it from the solution, right?
Yeah.
And then we can recalculate the Poisson bracket, and then to equate that, we can calculate the negative finite. Right?
Yeah. This part actually is the negative definite, which mainly means it is a dissipative part.
Yeah.
It is viscous.
Yeah.
Yeah.
But so I'm saying that it can be numerically calculated.
Yeah.
But
Yes.
it is not well defined per problem, so it will vary problem to problem.
I think there is a systematical way to handle that. Yeah. Yeah. The assumption here is this dissipative Poisson bracket is a negative definite. This is the only requirement you need. So if you use a split scheme, you handle the first part by some symplectic algorithm, symplectic integrator. The second part is you use some dissipative algorithm, right? Preserve the negative. Then I think it should be okay. Yeah. Okay, so this is the end of my talk.
Okay, thank you.
Thank you.
We'll move down to next screen for some conclusion, because it's coming summary, yeah. So open for questions. Lunchbox is outside, so is your questions answered?
Sorry, what's the answer?
No, your question answered or not?
Actually, if we know the vorticity, it is still not enough to know the velocity field, because we still need to have the divergence part of the velocity.
When you study with the freedom, it needs three flows. But if you know the velocity and the divergence, then you know everything.
Yeah. Then this is a Helmholtz decomposition for this. But in general, with the boundary, right? With the boundary, there's a Helmholtz Hodge and also Friedrichs and 3% decomposition with the boundary. Then it's depend on the topology. Yeah. So in addition to the divergence part, the gradient part, and also there is some part is a harmonic part, which carry the information of topology. If there is a boundary.
But you mentioned one again, and recently with some of my collaborators like Tepe here, we've been decomposing these vector fields, and you mentioned that already into helicities. So vorticity you can write as a sum of a left pseudoscalar and the right pseudoscalar. So if you write any vector field, you can write, of course, as a gradient. So Helmholtz is a gradient of a scalar, and then you usually say, well, curl of a vector potential, but that's not helpful because there's still 3 degrees of freedom, of which only 2 are independent. A more generic state decomposition is you say, oh, it's a gradient, it's a left gradient of a left pseudoscalar and the right gradient of a right pseudoscalar, and then you've got all 3. And again, under the Kelvin flow, all 3 are conserved. So if initially you only have left vorticity, then since once the flow, you will only have left vorticity and so on. So one of the open questions as people do in astrophysics is dynamo. So I'm ideal MHD, where some of this, I wonder whether that can be used, because it's one of the open questions as to why the sun and the galaxy and other things have magnetic fields at all. That's already, and why they change every 11 years. And it's thought that some people argue that this conservation of helicity is the driving element. So I don't know whether one could use any of these formulations to discuss conservation of magnetic helicity. Of course, that's more complicated.
Yeah.
MHD has even more equations, has 3 more equations, but or 2 more.
And the idea is balance theorem.
With magnetic
to
field.
some extent.
With magnetic field.
I was wondering here, just to think for later, of the conservation laws that appear in Hamiltonian mechanics. It was pointed out that Hamiltonian mechanics formulation, at least as written here, has to be outside of shocks. I think it's in between shocks. The theory can be done if I have a region bounded by shocks. Inside a region, those conservation laws will be valid. And we're wondering what will be the use of analyzing those quantities that are conserved between shocks.
The theory is valid away from shock. So between shock means it is valid, yeah. But if you cross the shock, then I think it is not valid. But how to modify the theory, I don't know. Yeah.
Even without modification of theory, gives huge information if it's valid between shocks. That's already plenty of information. Maybe not sufficient to solve the whole flow, but still useful information. The other question we'll have, it's probably a question that is a student's question to some extent, is I would like to think in terms of what will be a concrete example of the clash representation in Lagrange and Euler mechanics.
What is
the clash representation? Concrete examples of that representation. I'd like to think.
Yeah, clash variable. Yeah. Concrete example.
Yeah.
Well, it is a representation. Well, I think, I don't know. You can put some simple geometry and I don't. Yeah. Well, all the potential flow is one kind of clash variable representation. Yeah. It's V equal to gradient phi. So this and if it is also the incompressible flow, that is all the potential flow is an example. Yeah, and then you can add more. Then if there is a thermal effect, then you have a beta times gradient S. So which represents some thermal effect. And the beta dot equal to temperature. So you can add that. But then it is not enough. You need one more. So special case is the order potential flow.
Thank you.
Okay, so let's thank Professor Chern. So we can discuss other time later on and have lunch. Okay, thank you very much.
Okay.